third category of awardees fall under the category of humanitarian duty. Don Cohn once said that we should always find a better way. I think this definitely applies to this category of awardees. Scientists have a great opportunity to actually move the social barometer towards a kinder, healthier, and hopefully more just world. And certainly as it relates to health, our first awardee in this category, Nathan Schoepp, certainly meets that objective. I had the pleasure of meeting Nathan yesterday evening, so I know he's from California and has moved up and down the coast. He's a graduate student, as you can see, at Caltech, Pasadena, California, and he's only a few weeks away from completing that part of his career. And he didn't tell me to say this, but if anybody's looking for a good postdoc, you know, preferably in California, then he's your guy. Nathan actually, as award, relates to the development of rapid diagnostics to actually look at the susceptibility of antibiotics and antibiotics resistance specifically. He's been working as part of a project to look at devices and assays that can actually take place in the clinic at the point of care, so that we can actually either make sure the right antibiotics are given, or if they're not actually going to work, make sure they're not given and end up with even more superbugs in the world. So with that, I will hand over to Nathan to tell you more about his project.
All right. Thanks for that intro. That was very well said. It's an honor to be here and very humbling with all the people here and to see all the stories. So yeah, it's a real pleasure. So I'm going to talk to you about our work. Oh, that's good. Yeah. Really big one. Thank you. Is that better? Oh yeah, okay. I can hear myself now. Yeah, so I'm going to talk about our work over the past 4 years now, going on 5, working on developing a rapid phenotypic antibiotic susceptibility test, and hopefully something, so we work on the method primarily right now, but hopefully something that can be ultimately translated to the point of care and put on a device that your doctor could run in the clinic. So you've probably heard about superbugs and antibiotic resistance, so I'd like to give a little bit of an intro and frame where our work fits in that. It's a big problem, right? And I think you don't always think about the critical role that antibiotics serve in medicine, right? It's not just when you have a cold or an infection and you want to go in and get antibiotics and get cured, but really these things serve a much broader role. And anytime you have an immunocompromised case, so neonatal care, post-operative care, again, any sort of immunocompromised disease like cystic fibrosis, right? Antibiotics really enable all these treatments and procedures to happen. So like hugely important, right? Like modern medicine couldn't function without these drugs as we know it. And so resistance itself isn't the issue. Resistance is a natural phenomenon. It's going to happen the more we use antibiotics. I think they're really interesting drugs in that sense, actually. One of the few that the more you use them, sort of inevitably the less effective, less efficacious they become. The problem is really the rate of resistance and how fast it's spreading. And that's outpacing our development of new drugs. You've probably heard that in the media too, but that's really the core of the problem. And that's a whole separate issue, motivating sort of development of new antimicrobials and antibiotics that I'm not going to touch on today, but certainly something that needs to be worked on as well. So anyways, I put this up here just to show, it's from a 2016 sort of summary, the state of antibiotics, and it compares current mortality annually as a result of antimicrobial resistance, that's AMR, to some other high-profile diseases as we know it. And then if we continue on the current path we're on, the projections, conservative projections are, we'll reach 10 million deaths annually by 2050, right? And that's not that far away. I think, we're short-sighted in a lot of ways, but hopefully, this report and other literature like it can get us to focus sort of more long-term and realize that we need a better solution to this. On the right is another figure from this same talk, and I just put this up here again to say, I'm going to be talking about rapid diagnostics today, but there's no silver bullet, and this is a really, really big problem, and it's going to require increased public awareness, better sanitation and hygiene to prevent infections in the first place, better use of antibiotics in the environment, where you can really develop a lot of the resistance mechanisms that then get passed on to human pathogens. Vaccines and alternatives, again, to prevent infection, that's a really important one as well. And then just a general increase in human capital and sort of efforts towards this problem. And I think awareness is definitely starting to increase, and that's a great thing. There's things like the Longitude Prize and other prizes that are trying to incentivize better use of antibiotics. And so this problem has led to an international call from organizations like the WHO and the CDC saying, we need better diagnostics, we need more antibiotics, newer antibiotics, and we need just better use overall, right? Increased stewardship is the term you'll hear a lot. And so that's really the issue. Just to frame it a little more, what I'm going to talk about today, rapid diagnostics at the point of care. So what's really the problem at the point of care, and why is it important to have better diagnostics? So I made this little cartoon. I hope it's clear, but basically the issue is patient will come in with a bacterial infection, right? I'm going to talk about UTIs later. The physician, they go to the physician, they're going to prescribe antibiotics, right? In many cases, you don't have an option. There's no way to cure the infection without using antibiotics. But they have a choice. And basically their choice, they can choose a de-escalated therapy, meaning a first-line antibiotic, something that we've had for a long time. Maybe we want to use up, basically maximize its efficiency before we step up the therapy, which is shown here, or they can choose escalated therapy, right? And sorry, that's what I just described, where you're using like a second or a third line antibiotic, right? So for example, if you go in with a UTI, I like to use this example not only because it's the work we did, but I think it's something like half of all women will have a UTI by the age of 20, right? So it's a very common infection. In fact, it's the most common in primary care. The first question they're going to ask you is, have you had a UTI in the past year, right? And what they're doing there is just gathering empirical evidence and trying to see, okay, I don't know which antibiotic to prescribe, but how harsh do I have to be in my prescription, right? If you've had a UTI in the past year, they're going to be concerned it's a recurrent infection. They're going to step up their antibiotic therapy. The problem is, when you use that escalated therapy, inevitably, like I mentioned earlier, you get resistance. And as you go through this cycle, right, and then that can spread to other people or have a recurrent infection, you start to run out of antibiotics you can use, right? And so the more you use an antibiotic, the more you get resistance. And the issue, with superbugs is not that you have these organisms that are 100% resistant it's not that you have infections that are 100% resistant to all antibiotics. It's that the community levels of resistance are such that doctors don't feel safe prescribing any of the drugs we used to use, right? So they're basically out of safe options because they don't have the information they need when they're making the prescription. Okay, so this is kind of the cycle. And diagnostics can play this really critical role in giving physicians, if they're fast enough, the information they need to prescribe antibiotics and make informed choices instead of prescribing empirically, which is just based on the evidence at hand. Okay, so again, I talked about time already. I just want to really focus and show you some data on why we care. We've given ourselves the fairly arbitrary bar of 30 minutes, and there's no literature or physician you're going to speak to that's going to say it's got to be 15 minutes or under, right? It varies on a case-by-case basis. But in general, right, if you look at the numbers here, this is from a 2015 summary, the ambulatory care survey. You can see, right, most of the patient visits, you're only going to see the doctor for 15 to 30 minutes. Okay, that's a pretty clear peak. And so basically, if you're longer than 30 minutes, the chances that that test is going to be run start to drop off pretty rapidly, right? And ideally, right, it'd be even shorter. It'd be 15 minutes, but there's a limit depending on the type of test we want to do. That's sort of our bar. We're trying to get under 30 minutes because we think that could still actually be utilized. And then there's all sorts of other considerations I can talk about offline in terms of how simple it has to be to use and how fast and whether insurance companies are going to reimburse it and all these factors that go into actually making like a physical test that is going to be utilized. But timing is a big theme of today's talk, so keep that in mind. All right, so if you look at how antibiotic susceptibility testing is done today, there's two major ways. One is phenotypic, where you're looking at the response of the organism to the drug. And it's the most general method because you're actually exposing a viable organism that you've isolated from the infection to a whole range of antibiotics. And you're looking at does it respond? Does it grow or not? If it doesn't grow, we know the organism is susceptible and we can safely use that antibiotic. So this is general. It gives the physicians all the information they want, and then they can make completely informed choices. The problem is it's really, really slow, right? You have to first send the infection to a central lab, so the clinical sample, whether it's urine or some other fluid. They isolate the pathogen, they grow it up, they split it, they do broth or agar dilution like I'm showing here, expose it to a bunch of different antibiotics at a bunch of different concentrations. And then they, again, grow it up a second time. So that's a 2 to 3 day process at the fastest, okay? And so what ends up happening is that information isn't actually used. Again, because you go in, even in first world settings, right? And this varies, again, case by case, but in a lot of settings you go in, you see the physician once, they prescribe you antibiotics, and you're done, right? And it's not that they don't care about stewardship, they just don't have the time to send it out for culture and then make a call, change the prescription, right? That requires a lot of time on everyone's part. And so our goal is to really develop a test where they could have it, again, before they prescribe. The second way you might hear a lot about is called genotyping. So here you're trying to predict resistance. It works in certain cases where you have a single gene that's responsible for coding, for a protein that gives the bacteria resistance. But in general, it's not a very general approach, and so it also hasn't really been adopted to the levels that can really make an impact in terms of antimicrobial stewardship. And so this is just showing this plot. The number of known beta-lactamase genes, that's one mechanism of resistance against one class of antibiotics. And as of 2010, there's 800 known genes. So to design a molecular assay that could screen for all resistance genes known, not to mention the ones we don't know about, is pretty much impossible, and that's what leads to the lack of generality. So again, there are specific cases there I can talk about later, but in general, you have issues with both, right? It's either too slow or not general enough, so we have to address both those challenges. So going into this, our hypothesis was that maybe we could use nucleic acids to measure the phenotypic susceptibility of bacterial infections. And so our thought was, if the antibiotic is going to impact replication and ultimately growth, the sooner we can pick up a difference or pick up that impact, the sooner we can call that infection as susceptible. So we need viable organisms. We're going to do an antibiotic exposure, and then we're going to look at the nucleic acid concentration. And so this is actually very exaggerated in terms of the actual ratios that we're observing. I think you'll see that in the next slide. But basically, right, if they double, then you get a ratio of 2 between the control and the treated sample. So the control sample has no antibiotics, treated sample has antibiotics, and we're just comparing the total DNA concentration. We're not looking for a specific gene, we're just trying to measure concentration very precisely. And then obviously another doubling. And so the sooner we can pick up basically if there's a difference, then a difference in the control and treated, we can call it susceptible. If we don't see any difference, we know the pathogen is resistant. And so this was our hypothesis going in. I'm going to skip a bit of the developmental work and just show you sort of some final numbers from the first sort of story. And this is for 4 classes of antibiotics, the 4 main classes used to treat UTIs. Again, we didn't do any clinical work here. We'll talk about that next, but we sort of were forward thinking in the antibiotics we wanted to test. And what you might be thinking is, well, what if the antibiotic doesn't impact replication, right? Then how are you going to get a difference in DNA concentration? And that's exactly what we thought and exactly what we tested these for. And you can see if you make the measurement precisely enough in all your susceptible isolates, so these are clinical isolates isolated from people with infections, that are known to be susceptible to the antibiotic we're testing, you always see a difference in the fold change, again, between 0 and 15 minutes is what you're looking at. And then in the resistant sample, you don't see any difference. And that holds up across all 4 antibiotic classes. And what we were excited about here was that we could shorten the exposure time. Again, I kind of skipped over that a little, but we tested how long do you have to expose the pathogen to antibiotics before you can pick up this difference, right? If we have a half-hour window, right, and we're trying to look at a biological response, we better be able to make that measurement really quick, because if we have to expose for an hour, that test isn't going to work no matter how fast our readout is. And so this was exciting. This is after 15 minutes of antibiotic exposure. There was sort of an interesting story with amoxicillin. That's a beta-lactam. It affects the cell wall, right? Does not have any immediate impact on replication. But what we found is that because of the readout method we were using called digital PCR, where you partition all your molecules into basically droplets. If you were careful about the way you handled the DNA, we still get this big change, and what we think is going on there is a difference in actually how the chromosomes segregate in bacteria. But don't worry about that, it's sort of a side story. Basically, the important takeaway is that for multiple classes of antibiotics, regardless of the mechanism of action, we can still pick up a difference. Okay, so now we wanted to think about clinical context and how we're going to test this. And I hope none of you have seen as many clinical urine samples as I have, but if you haven't, this is really what they look like, right? So you get a whole range of turbidity and precipitates and blood and all sorts of things in urine. These are UTI samples. We collaborate with the UCLA microbiology lab. And I just show this to sort of give you a sense of one of the challenges we were up against. And urine is actually a relatively simple matrix to work with in terms of biological samples. But anyway, so another reason we chose urine was because it has to be, so I already mentioned, it's the most commonly encountered bacterial infection in primary care. It's always treated with antibiotics, because if you don't treat it, it can progress, this is UTIs, can progress to pyelonephritis, which is kidney infection, and even urosepsis, which is one of the main causes of sepsis in general, which I learned recently, which is interesting. So you have to treat it with antibiotics. There's a ton of antibiotics being used. It's a relatively simple matrix to work with, and again, the matrix of antibiotics and pathogens that we have to worry about is also sort of decreased. E. coli causes 80% of UTIs. So we thought, okay, if we can develop a test for UTIs or a methodology that could be translated to the clinic, that could be pretty immediately impactful on antibiotic use. But again, we're up against this challenge of working with actual clinical samples and all the junk that comes with them. This is what the workflow looks like. I sort of alluded to it earlier, but we take a UTI sample. We always split it, right? Because we're looking at the bacterial response. We're measuring the phenotype. And we have a control, and we have an antibiotic-treated tube. And then we measure the DNA concentration after exposing the treated sample to antibiotics and incubating these both for 15 minutes. And you get one of two outcomes. Either the pathogen you were looking at is susceptible, and you see a difference in the DNA concentration because the antibiotic has inhibited replication in the treated sample, or you don't see any difference, and that pathogen is resistant. We then take a ratio just so we can get a single number out, and you can then test a bunch of these things, draw yourself a threshold, and then start measuring unknowns and saying, okay, where does the ratio fall? And you can make a susceptibility call based on that. And you can do that for multiple antibiotics at once if you want to. So this is the workflow. We've got clinical samples now. They were coming in daily, and we were testing these. One of the first questions we wanted to ask, so we're looking at DNA, and so everyone here is real familiar with that, I imagine. So we knew we had molecular specificity, and we wanted to sort of prove that this is an advantage over, say, a microscopy technique or some of the other techniques out there. And so what this is looking at, this is a single susceptible E. coli isolate and a single resistant E. coli isolate. And we did our test in the presence of 3 different concentrations of a common commensal organism called lactobacillus. And even at 10x the concentration of lactobacillus, because we're targeting only the E. coli DNA and only looking at the effect of the antibiotic on E. coli, we can still get, in all cases, difference, 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 no difference, no difference, no difference, and our ratios come out almost identical. So that was really exciting, and was sort of to address what we think is one of the major challenges. Again, I mentioned all the junk in urine. Well, you have other bacteria in urine that aren't necessarily harmful or infectious. And so you have to get around that. And so this was, again, exciting and showed sort of the power of molecular techniques and their specificity. Okay, so next, how did our test do? We tested just over 50 clinical samples using 2 different antibiotics, a first-line and a second-line antibiotic, ciprofloxacin and nitrofurantoin. This was, again, I couldn't go over the details of the development of the sort of readout part, but that took a lot of work, and happy to talk about that after. But basically, once we had that, we do a short exposure, we do the readout, and we get pretty good results. So these are a bunch of known susceptible samples, a bunch of known resistant samples. We run our test, we look at that ratio, we look at how they group in each category, and what you hope is that you have really nice separation so that your susceptible will always be above the threshold you draw, your resistant will always be below. And indeed, we have a couple errors, which is fairly expected, but overall, if you plot what's called an ROC curve, a receiver operator characteristic curve, it basically tells you on one plot your sensitivity and your specificity. People look at the AUC a lot. 0.95 is really, really great. It just means we don't have a lot of errors, which you can see in this example pretty easily. So that was exciting. These were clinical samples run directly using our method, right? So that already is very encouraging that we could take this and translate it to a point-of-care device. But one final thing we wanted to sort of prove to ourselves, and why I spent a little bit of time talking about timing of the assay up front, was can we really do this in 30 minutes? So there's a lot of data on this slide. I'm going to walk you through it. But basically, we had read, at this time, so many papers claiming that they have a rapid AST, right? But the challenge, like, if you have a 4-hour AST, that's rapid compared to 2 or 3 days. But that's not rapid for the point of care. That's never going to be used, right, when the patient is waiting, because no one has that sort of time to wait at the clinic, especially if you're at, these outpatient clinics or STI clinics, right? Like, these have to be really rapid turnaround times. So we wanted to prove that we could take this sample, run the test actually in half an hour, right? And so this was us running through the lab with samples. As soon as we put it into the control and treated tubes, we started a timer. And again, this is just showing the workflow and a bunch of the data, also that I thought a lot of people here might be interested in. So clinical sample, we do our split. We do a very rapid DNA extraction. And then we quantify. This is using, again, digital, in this case, digital lamp, meaning digital means you split up all your molecules. And then you amplify them all at once, and you count how many positive partitions you have. And so you're really counting single molecules, and that's what gives us the precision we need. LAMP is an isothermal DNA amplification method that a lot of people at NAB, I think, are really familiar with. And it's super powerful in that, when optimized, you can take single DNA molecules and amplify them up to something you can read out in 5 to 6 minutes, which I think is incredibly powerful. You can't do that with a lot of single molecules of any sort. And so that really gave us a lot of power. So we measure the control and the treated sample. And again, you get one of two outcomes. Again, these are each curve. That's a single DNA molecule being amplified. And that's just a subset of the 1,200 we amplify all at once and measure. And either you see a difference in your concentration. As soon as we see a statistically significant difference, we can call that sample the susceptible. Or the concentrations don't change over time, and we know that sample is resistant. And so, again, we take the ratio. And then one other final part, which I think a reviewer brought up, we realized we had this 15 minutes of antibiotic incubation that we weren't really using for anything, right? But in a half-hour test, we want to make the most of every minute, literally. And so during that antibiotic exposure, we extract sort of a separate aliquot, again, do a real rapid extraction, amplify again using that same methodology I mentioned, LAMP, and then we can ID the sample as either E. coli or not E. coli, right? Or you can design primers to identify it as whatever you wanted to, whatever bacterial species. And so this was just important because right now physicians are real focused on sort of you ID the bug, and that tells me how to treat it, and then you run the AST if you have time, right? But in theory, you could just run the AST, because if you had that information, it doesn't matter what the bug is. But because, again, they care a lot about the ID step, we put this in, and just to show sort of how easy it is, and again, with the power of these molecular assays, how quickly we can amplify DNA and identify things or measure a response. Okay, so I just want to show you, we made those digital measurements I mentioned on a microfluidic chip that looks just like this. They're made of glass. We actually collaborated with the startup that's manufacturing these from plastic. And they've licensed some of our patents too to work on the AST stuff. But I just want to show you what it looks like. This is slightly accelerated, but you can see the time. It's not much. And so these are, again, single DNA molecules being amplified. We're counting them in real time, and that is what is telling us if the bacteria is susceptible or resistant. And this was a susceptible sample. You can see the control clearly has more DNA. It's continued to replicate. The treated sample has stopped replication. And so we can make a call really easily. And then we automated the system to read this out. And so right now, maybe I won't, well, I'll keep it looping. Right now, we need one treated sample for every antibiotic, right? And this chip isn't that big, but you can imagine you'd have to put 8 of these on the bottom of some sort of device that does the incubation and then the DNA extraction. Overall, pretty simple workflow. We don't have the device yet. We've got people working on devices in the lab. But what we're also thinking about is some different assays to read out concentration on the back end. The only issue is we have to make a very sensitive measurement of concentration. So something like qPCR, like exquisitely sensitive, but not quite sensitive enough on these really short timescales. Okay, so the current 2 directions over the past 2 years are carbapenem-resistant Enterobacteriaceae, which is a whole family of really nasty infections that's very resistant to many classes of antibiotics, and Neisseria gonorrhea, which causes the infection gonorrhea, which you've probably heard about as a superbug. And again, just to be clear, the problem is not that most infections aren't susceptible to one antibiotic. The problem is the overall rates of resistance for all those antibiotics have risen to such a point that doctors can't safely prescribe drugs. And so if you had a diagnostic like the one we just showed for UTIs, for gonorrhea, you're re-enabling use of all those past antibiotics, right? You could treat with penicillin. I don't know if you've seen these ads, right? Like penicillin cures the clap from like 1940s. But that's the power, is that it's not only giving doctors the information they know, but now they can use more drugs. So it's in a way sort of reinventing these antibiotics and allowing their use. I also want to thank the team, past and present. Travis was co-author on the UTI work. I'm working with Emily on the gonorrhea project, Eric on CRE, and then these people were instrumental in founding a lot of the work. That's my PI, Rustam, and Matt is a new MD student in the lab, also working on gonorrhea. And that is that. I'd love to take any questions.
Any questions for Nathan? The front?
Yeah.
Ned, that was a great talk. I was wondering, in terms of when this becomes successful, how much do you think it will cost? Especially given that you don't want to just keep this in the United States,
right.
Looking at places like Africa, is it something that can be adopted?
Yeah, that's a great question, and one we get, I'm glad to say, often, which is, and because it's really important. So we focus on the methodology, right? So I can't tell you a number, but I can tell you that compared to a lot of other methods out there, which is sort of how we're always placing ourselves, right? Mm-hmm. We think the workflow is simple enough that it could actually be translated and used in, sort of more rural clinics, right? Because all you need, there's an exposure step, mm-hmm. there's an extraction step that uses a commercial reagent. It's a surfactant and a protease, mm-hmm. And then there's the amplification step. And so, again, there's a company working on making those microfluidic chips more and more cheaply. Mm-hmm. But again, if you could convert that to some sort of competitive assay, or we've got lots of ideas there, then I guess what I'm trying to say is all I can speak to is that it's a very simple workflow, and that's what encourages us the most, right? There's no, or not necessarily, there doesn't need to be a microscope involved, there doesn't need to be a mass spec involved, and so you could really think about having a very portable system that does this. Yeah. Stephen?
So if I got this right, you're measuring replication in general, and
right.
You brought up the point that we're covered in bugs and we have a consortium, right?
Right.
So all these things could replicate. So I'm guessing that the specificity was that your amplification, you made a comment that most of the time it's E. coli.
That's right, yeah.
So what if it's not E. coli?
Yeah.
So you said at the end, at the back end, you could do some identification, but then you'll be measuring replication is of course not going to show up in your assay, or it's going to show up selective, but that's not driving the infection.
Right.
How do you deal with that problem?
Yeah, it's also a great question. So our specificity comes from the primer design. And so in this case, we can design E. coli specific primers. You're right, I did say the ID a bit out of order, but the thought would be you do the ID step first, right? And so you have an array of primers designed for multiple pathogens. Identify the pathogen, and then either add on, even though that's already too many steps, right? I mean, this needs to be like push button and go, but it would automatically route it to then the correct primer set for the AST, right? And those can be the same, but yeah, it's a great point, and I didn't mean to make ID sound unnecessary when these things are starting and you're validating, right? That's definitely going to be the workflow, is you do an ID step first, followed by an AST. Yeah. Yeah.
So E. coli is really nice to play with like this because you get a nice short division time. So I'm a symbiosis beneficial bacteria person, but are there pathogens that take a lot longer to have that first division? And will a half hour be doable?
Yeah. I'm really glad you asked that. And it's a great question. So gonorrhea is a perfect example, right? Under optimal lab conditions, its doubling time is 60 to 90 minutes, right? And so even to get a fold change of the best we can detect with our digital assays is maybe a 20% difference, right? You still need way too long. You still need to incubate for half an hour at least, right? And that's under optimal conditions. In our experience, it's actually much slower. And so what we've come up with, right now we're focusing on beta-lactams for gonorrhea, which are historically the largest class used to treat gonorrhea, and the last line treatment that we're on now is a combination of a beta-lactam and a protein biosynthesis inhibitor. And so they're a real important class, and what we can do is play some tricks. So with the beta-lactams are going to hit the cell wall, and we can basically use, by including other reagents, the papers are coming out real soon, but I can tell you more details after personally, but we can impact the nucleic acid concentration based on the state of the cell wall. Right, so you can probably piece together, a version of what we're doing, but we still can use readout on the back end, which is specific and fast. But now we only have to incubate, incubate for again we're at 15 minutes right now because cell wall replication occurs, a little bit. We don't need to double cell wall replication to get a readout, right? As soon as you start impacting it, which is almost immediately with most of these drugs, then we can do our assay. Yeah, it's a really great question. And E. coli, great for UTIs, which is why we picked UTIs, but pretty much the fastest bug out there. So what are you going to do when you hit slower things? And so we've had to come up with other methodologies. Yeah. But yeah, our cap is still half an hour. That hasn't changed. Yeah.
One final question.
On that same note, a lot of us have been thinking about these point-of-care diagnostics for a long time. And while we have been, there's been a development sort of in the background, which is the fact that most patients, when they come in, will leave before they get the diagnosis.
Right.
But there has been this transmission of the prescription to the relevant pharmacy that happens even after the patient has left. And that sort of takes care of this problem.
Right.
In my mind.
So I guess it depends on how long after, right? I mean, if physicians are willing to change that 2 days after, then that absolutely solves this problem. And we're sort of coming at it from an approach of thinking about the scenarios where that doesn't happen, where they don't have a relationship with that patient, they see them once, and even if the patient leaves, as long as they can run this in the half hour and then write their prescriptions at the end of the day or whatever it may be, then we think it could still make a big impact because, they're still, you talk to physicians now, they're still prescribing empirically, right? They're not making informed decisions, and you can't blame them, right? They all know about stewardship, and that's important, but they also have patient outcome to balance, and I think you're never going to trump that unless you can safely prescribe a de-escalated therapy. Yeah, but it's also a good point.
Great. I'd like Nathan to stay up here to receive his award.